There we go. Oh. Okay, now we're ready. Hi, everybody. My only announcement really is that the next Achieve homework is due on Monday. This is the first part of Chapter 3, so it's all about nomenclature and writing molecules and things like that. The second half of Chapter 3 will be posted on Monday for you all to complete. And that's it. I'll have your exams ready for you sometime next week, probably Wednesday or Friday, just so you all know. All right, that's it. So let's remember what we talked about on Monday of this week. We talked about the difference between ionic and molecular compounds, where ionic compounds, let me go back to this slide, all the way in the beginning. Ionic compounds are repeating units of the formula unit, and they exist in a lattice structure, and we have two ions. We have negatively charged chlorines and positively charged sodiums. And then in molecules, one formula unit is the entire molecule. We talked about naming molecular compounds, and then a little bit about ions. So we talked about how we have all of these polyatomic ions. Polyatomic ions have covalent bonds within the ion, but because they exist with a charge, they then have an ionic bond with another atom or another polyatomic ion. So, for example, in the NH4 molecule, there are covalent bonds between the nitrogen and the hydrogens. But if you have something like NH4Cl, we have NH4 plus, Cl minus. That's an ionic bond between the polyatomic ion, cation, and the anion. This was where we ended, so we were just writing the formula for the compounds for a metal and a polyatomic ion. And so something is called or considered an ionic compound if it has a metal and a nonmetal. We've talked about that before. So sodium chloride, magnesium bromide, there's a metal and a nonmetal. Those two are bonded together through ionic bonds, so it's an ionic compound. It's also considered an ionic compound if we have at least one polyatomic ion. So this first example is a good example of where we have all nonmetals, but NH4 on its own is a cation, and Cl minus is an anion. So this is an ionic compound between the NH4 polyatomic ion and the Cl minus. And then this example here, we have a metal polyatomic ion, so we have an ionic compound. So let's just spend a minute or two working on the slide. It's not an iClicker, although I did start the class, so you should pull up iClicker and join for when I do have an iClicker question for you. But for now, just work on this slide identifying which ones are ionic. All right, let's start going through these. We first have carbon tetrachloride. Remember our naming binary molecular compounds. This is a name of a binary molecular compound where we have carbon and we have 3 Cl atoms. It's not letting me draw. One sec here. May have froze. Okay, hopefully that will not be an issue again. Okay, so we have carbon and we have 4 chlorine atoms. We have 2 nonmetals. Both are not ions. And so this is not an ionic compound. In the next one, we have lithium, which is a metal. So we already have a metal. We know right away this is an ionic compound. Periodate is a polyatomic ion. So this is in your list of polyatomic ions. Either way, we have a metal. We got an ionic compound. Next, we have magnesium bromide. Magnesium is in column 2 of the periodic table. This is another metal. If we have a metal, we have an ionic compound. Sulfur dioxide. Sulfur is a nonmetal. Oxygen is a nonmetal. So these two together do not form an ionic compound. They form a molecular compound. And then last we have calcium carbonate. Calcium is a metal in column 2. Carbonate is a polyatomic ion. So again, ionic compound there. Any questions about these so far? Okay, let's go the other direction now, where we are, well, not really the other direction, but let's look at a name of a compound and then actually write out the entire formula. So to write formulas for ionic compounds, when you're given the name, know that the cation to anion charge ratio has to have a net charge of 0. So we use the charges of what's part of an ionic compound to determine how many of each atom or each polyatomic ion are needed in the formula. We always list the cation before the anion, so positive charged part of the compound before negative. We write the formula of a polyatomic ion as a unit, so we don't separate any of the atoms that are part of a polyatomic ion. And if we have more than one polyatomic ion in the ionic compound, we put parentheses around the polyatomic ion and use a subscript at the end to show how many. And we've seen examples of this in the past. But let's do these examples. So we have magnesium bromide. Magnesium, if we look for it on the periodic table, it's in the second column. So it has a 2+ charge. Bromide is in the column 7A or column 17. It has a -1 charge. So to cancel out 2 positives and 1 negative, we need 2 negative charges, so we need 2 bromines. So this formula is MgBr2. The next one we have ammonium nitrate. Both of these are polyatomic ions. So we look to our list of polyatomic ions to find the charges. Ammonium, this is a good one to just commit to memory, NH4 plus. Nitrate is NO3 minus. We have +1 from NH4, -1 from NO3. So these are balanced already, and we write NH4, NO3. Yes. The NH4 is a polyatomic ion with a +1 charge. NO3 -1. Or NO3 is a -1 charge.
Would it be wrong to combine the nitrogen?
I love that question. Would it be wrong to combine the nitrogens here? Then we could do N2H4O3. That is wrong because this is its own polyatomic ion. These atoms are bonded together as NH4. This is its own polyatomic ion. Atoms are bonded as NO3. Then they have an ionic bond between the two polyatomic ions. But keeping them separate demonstrates that these are two polyatomic ions. So that is step 3 here. The formula of a polyatomic ion is written as a unit. So we always keep those atoms together as they are written for the ion. For our last example, calcium phosphate, we have calcium again in the second column with a +2 charge. Phosphate, if you look on your periodic table, not on your periodic table, on your list of polyatomic ions, it's PO4 3-. To balance charges, we need 3 calcium cations and 2 phosphate anions. You can find this by doing that, I forget what you all call it, cross and cancel or something. The charge on this one is the subscript for the cation. The charge on the cation is the subscript for the anion. Or you can just think about balancing charges using the least common multiple. We need 3 calciums, and then in this case we use parentheses to denote that we have 2 phosphate anions, and the 2 applies to the entire phosphate molecule. Okay, questions on these? Yes.
So why don't you need parentheses for like the second one?
For the second one, we only have 1 of each, and we don't use ones when we write out molecular formulas. So if we had used parentheses and put a 1 there, that implies the same thing as not using parentheses. So if we don't need parentheses, we don't use them. Good question. Yeah.
So one, the magnesium doesn't have 1 in the first one, so what is that?
The magnesium doesn't have a 1, so we don't need parentheses. And then the bromine we only need parentheses for polyatomic ions. So like phosphate is PO4 3-. So if we need 2 of them, we need 2 of the whole ion. So we keep the ion as a unit and use parentheses to say the 2 is for the entire.
Okay, so it should always have a parentheses with that, the phosphate.
If there's more than 1. Yeah. If there's only 1, then we wouldn't. Yes.
Do you have to know like the charges for that?
For polyatomic ions? Probably not. I will let you know if you need to remember any. Like I said, I think NH4 ammonium, like knowing the name ammonium is NH4 plus, good to remember. That's just an extremely common one. I'll let you know if there are any others. I can't remember if that's required or not. All right, let's do this next question. I think the first one is an iClicker, so let me push this to your devices, or you're typing out the formula. So we have 2 ionic compounds. Let's spend a minute or 2 working on that. Say 1 more minute and I'll close the iClicker. Did you log out of that? Okay, I'm gonna close it shortly. Yeah. Good question. We'll talk about that. All right, I'm going to close it. And let's see what we're thinking. Oh, you can do a subscript. Okay. First one, we have sodium oxide. We have sodium, which has a +1 charge. Oxygen has a -2 charge. Those are charges that you certainly should remember, the ones that do not change based on where the atom is located on the periodic table. To cancel out charges, we need 2 sodium atoms, so our molecule is Na2O. There's a question, should we include the charges or not? So when we write out ionic compounds, we don't include charges because they cancel out. But in an ionic compound, remember that they are made of ions. So the sodium does have a +1 charge. The oxygen does have a -1 charge. But ionic compounds are typically written out without any charges. For our second one, we have magnesium nitrate. Magnesium +2 charge. It's in the second column. Nitrate is a polyatomic ion, NO3-. We need 2 nitrates to balance out the magnesium 2+. So the formula is Mg. In this case, we need to use parentheses to show that the 2 nitrates applies to the entire nitrate polyatomic ion. And that's the ionic compound, or the formula for the ionic compound. Now notice in this first example where we don't have a polyatomic ion, we have 2 sodiums, but we don't use the prefix di for the sodium. So this is a difference between naming the binary molecular compounds and ionic compounds. When we have more than one ion, we don't use those prefixes. So that's what this next section is about, is just naming our ionic compounds. And this is the last section before we move to part 2 of chapter 3. So we have slightly different rules for naming ionic compounds, still quite similar to what we've learned already, and we've seen plenty of examples of ionic compound names. But one key piece of information to remember is if the cation has a varying charge. So anything in the first column is always +1 charge cation. Anything in the second column is always +2 charge cation. And then we have 4 over here: aluminum, zinc, cadmium, and silver. Those all just stay the same. So if only one cation can form, the charge of the cation is not indicated in the compound name. But if we have any cation that's in this section, so basically almost all of the transition metals except for a few, then we need to indicate which charge it has for that specific compound. And so we do indicate that in the name when we write out the actual name of that compound. So I have a flow chart and then some information on future slides and then a bunch of examples. So this flow chart, I feel like I need a laser pointer. Looking at the one on the left, we have an ionic compound. We start with looking at the cation. If we have a cation in row or column 1, column 2, or the other 4 on the other side of the periodic table that have a constant charge, we just write the name. If it's an element that has a varying charge, we write the name of that element, and then in Roman numerals, the charge that that element has in that compound. Usually it's 1, 2, or 3, but it can be higher. And then the anion, if it's a monoatomic anion, so not a polyatomic ion, we write the root of that element name, and then we end in "-ine", just like we do for the binary covalent, like sulfide, oxide, things like that. If it's a polyatomic anion, then we just write the name. So here are 2 examples. Calcium chloride. Calcium is in the second column. It has a constant charge of +1, so we just write calcium. Chlorine is a monoatomic anion, so we write chlor for the root of the name and then "-ine" at the end. Even though we have 2 chlorines, we don't use di here because we know that these 2 atoms have a constant charge. We know that we need 2 chlorines to balance out 1 calcium. So that information is already stored in the name. We don't have to specify it for ionic compounds. Here's an example where we have a cation with varying charge. We have iron. We have iron sulfate. So iron has a variable charge. We write the name iron and then Roman numerals in parentheses to show iron has a +2 charge in this compound. And then our anion is a polyatomic anion, so we just write the name of it. We don't put "-ine" at the end here. Now, we can tell the charge of the cation that has varying charge by looking at the anion. So if this is SO4, and iron and SO4 are in a 1-to-1 ratio. SO4 has a -2 charge, then iron better have a +2 charge to cancel that out and make it a neutral compound. So that's how we know it's iron 2. Okay. Emphasizing or just explicitly writing all of this, if more than one cation can form, we indicate the charge by adding a Roman numeral in parentheses immediately after the cation's name. Two examples at the bottom of the page there. And then the charge of the cation is determined by considering the neutrality of the ionic compound. So remember, charges must cancel out to be neutral overall, and anions don't have varying charge, so we can always look to the anion to determine the charge of the cation. So here are two examples down here. Copper oxide, we have one copper and one oxygen. We know that oxygen has a -2 charge that never changes, so copper is +2 for this example. In the second example, we have two coppers and one oxygen. Oxygen is always -2. If we have two copper atoms, then in this molecule, the copper has a +1 charge. So the +1, having two of them, +2 overall, cancels out with the -2 from the oxygen. Okay, questions on this so far? Okay, the next two slides are some special, I guess, ionic compounds, and then we'll do practice. So there are some ionic compounds where between atoms of the ionic compound, water molecules are stored within gaps in the ionic compounds. So copper sulfate is an example. Copper sulfate pentahydrate. There's copper sulfate in that lattice structure, and then in spaces between atoms, there's water molecules. And for every unit of copper sulfate, there's 5 water molecules. This is what it looks like. It's like a little blue powder. So these are hydrates. Hydrates are ionic compounds that have water molecules incorporated into their solid structures. So the name of any hydrate is the name of the ionic compound followed by a Latin prefix and then the word hydrate. The Latin prefix indicates the number of water molecules. They're the same prefixes that we use for the binary covalent compounds, so di for 2, tri for 3, tetra for 4. So the formula for any hydrate shows the water for the hydrate separate from the ionic compound, and they're separated by a dot in between. So there's this dot, there's the ionic compound first, and then the number of water molecules second. And then a coefficient before the H2O indicates the number of water molecules in the formula. So here's copper 2 sulfate pentahydrate. That penta is a Latin prefix, hydrate at the end for water, and then copper 2 sulfate is the name of the ionic compound. Where, wait, can you say that? Oh, right here? No, this is just saying this can be monohydrate, dihydrate, trihydrate. It's a Latin prefix right there. Okay, so these are hydrate molecules. And then here we have oxoanions. So these are anions that have oxygens as part of the anion. So we have one element and then oxygen. These are listed as polyatomic ions, but there's also a systematic way of naming them when we have, well, we'll go through it. There's a systematic way of naming them. So the name has a root taken from the name of the central atom. So in these first two examples, we have carbonate. This is a carbon atom in the center, and then oxygen, oxygen, oxygen. So we have carbon, 8 carbon is because carbon's in the center, or nitrate, nitrogen is in the center. So we have the first part of the word to represent nitrogen. if an element forms more than one oxoanion, so in this example, we have a sulfur. So the element sulfur can form an anion with 3 oxygen atoms and an anion with 4 oxygen atoms. The anion with fewer oxygen atoms ends in ite. So the ITE here, we have sulfite. And the one with more oxygen atoms ends in ate. For halogens specifically, they can form 4 oxoanions. So the naming here is shown for chlorine, but this would apply for bromine and iodine as well. So if you look in the center, we have the 2 that align with what we just talked about. ClO2 minus is chlorite. ClO3 minus is chlorate with an added oxygen there. If we add another oxygen, ClO4 minus, we have perchlorate, so now we have a prefix there to indicate that there's an additional oxygen. And then if we look at chlorite, and when we remove an oxygen, we have Cl minus, we have hypochlorite. And then lastly, if we have a polyatomic ion that has a charge more negative than -1, a hydrogen cation, so H+, can be added to give another oxoanion. This is named by using the name of the parent ion without hydrogen and then adding hydrogen to the beginning. So we have carbonate at the top here, CO3 2-. If we add a hydrogen with a +1 charge, we now have HCO3-. We have only -1 here because the hydrogen was +1. And then this is named with the word hydrogen first, and then the name of the group ion, so hydrogen carbonate. In this example, we have 2 hydrogens. We have dihydrogen phosphate. And then in this particle image here on the right side, we have carbonate, and that which is CO3 2-. If we add a hydrogen, we have HCO3-. See that hydrogen is added here, hydrogen carbonate. Okay, now do we have questions? How about one question? Someone asked me one question. Thank you. Yes. Sulfate. Oh, but if it was per sulfate, it would be SO5. I don't know if sulfur can form that anion though. I think it's only our halogens that can do that. But yes, if you were at sulfate and you have an additional oxygen, then it would be per sulfate if it's possible to form. I don't know if it is. Okay, thank you. I got a question. I'm happy. We can move on to the learning check. So these next 2 slides are just a bunch of practice naming molecules or writing formulas or determining if you have an ionic or molecular molecule. There are 2 on here that will be pushed as an iClicker, but first go to this table. In change methane, because we didn't talk about methane, change it to iron 3 phosphate. This one here. Oh. Okay. So 2 from the previous slide are pushed as iClickers. Work on those, work on the rest. I'll be walking around if you have questions as you're working, and then we'll go through all of these. You're putting in Roman numerals, just use the letter I.
Yeah, because the two, like, because sulfur has a negative charge, and so to make it clear, yeah. So since magnesium, we know the charge, that means that's one. So you just gotta know that. Or, that's
For all of them, yeah. Yeah. Oh, I answered to quickly. Yeah.
So, the hydrates were not the same as hydrolyzed. So that thing. So it's isn't those the water that's
Yeah, so that would be because if we added ion two when I added water, like sodium chloride, when it's hydrolyzing, and it converts into sodium plus calcium.
so it dissociates. But this is just. There we go. That's weird.
Almost there, but magnesium is the second highest It always has the most charge, so we don't have to predict the number.
Fluoride is just fluoride, and then it's just like, no, that's not what I was thinking of. Yeah.
So like this one of them. Are we ready? You want another? We're ready? Okay. No? No, we're not ready. All right. One more minute and we'll start going over these. All right, I'll end it in 5 seconds. All right. Okay, first we have copper and sulfur. So copper, and then how do I name the rest of the name? 2. I need a 2 because copper is one of the elements that has a varying charge. And how do we know it's 2? Because, yes, sulfur has a -2 charge. So copper, to cancel out the charges, have a neutral compound, must have a +2 charge. Next we have iron. This is another element with a varying charge. In this case, we have to work backwards to determine what the charge is. If we do the cancel out cross method, whatever that's called, you can determine it's iron 3. So we have iron 3 oxide. Oxygen has a -2 charge, iron has a +3. That would give us the appropriate number of each atoms to cancel out charges. Next one, we have magnesium. Do I need parentheses here, the Roman numeral? No, why not? It doesn't yet. Yes, it doesn't have a variable charge. Magnesium is in the second column. It's always a +2 charge. So we don't need to write its charge. So we have magnesium, and then we have 2 chlorine atoms. So we write magnesium chloride. We have 6 water molecules. So magnesium chloride hexahydrate. Next, we have a polyatomic ion. This polyatomic ion has a halogen bromine, 4 oxygen atoms. This follows the per bromate rule. That's the name of it, per bromate. This is in our list of rules on the page for oxo anions. Just like this right here, ClO4 is per chlorate. So BrO4 is per bromate. Questions on these? Yeah. Both are correct. Yeah. Anything else on this one? Okay. On this table, we start with NO3. We've seen NO3 minus as a polyatomic ion, but this NO3 does not have a charge, so this is not an ion. It's not the polyatomic ion nitrate. It's a molecular compound. So we name this using our binary molecular compound rules. We have 1 nitrogen. We have 3 oxygens, so nitrogen trioxide. Remember, if we have both nonmetals, we use a prefix for both of them to demonstrate how many are there. So this is molecular. Barium fluoride. Barium has a +2 charge. Fluorine is -1. We need 2 fluorines to cancel out the barium +2. This is a metal and a nonmetal, so it's ionic. Next we have CaCl2. Element Ca is calcium. Cl, of course, is chlorine. We don't use a prefix when we have ionic compounds, so calcium chloride. And then this is ionic. Iron 3 phosphate, we have iron, and if you look up phosphate, it has a -3 charge, so these combine in a 1-to-1 ratio. We have FePO4, ionic. Okay, we'll finish this. We're past 11:50. I'll respect your time. We'll finish this on Monday. Then we'll start the second half of chapter 3, which is a separate PowerPoint. Make sure you bring that to class Monday.